Welcome back for part 2 of our discussion on differentiating the inverse trig functions. And in this video, we're going to jump right into differentiating arcsine. And when we're asked to differentiate y equals arcsine x, this is really just a fancy way of saying for this expression, find dy dx. Now there are at least two possible approaches. One would involve going back to the definition of the derivative. And I think if we're all pressed, we would prefer not to have to go back to that definition. The other approach that we've seen recently is using properties of inverse functions along with implicit differentiation. That is, can we maybe take the same approach we use to differentiate the natural log and apply it to differentiate the arcsine? So starting with our expression y equals arcsine x. So a bit of intuition. When I look at this expression and I think about differentiating, I have no idea how to differentiate arcsine. Maybe in a few minutes I can't make that claim, but for now we do not know how to differentiate arcsine. But if I could rewrite this expression so the troublesome term was not present, then we might be able to differentiate. And note, this is something we can very easily do. Let's just take sine of both sides. This would imply sine of y is equal to x. And now that we have sine of y equals x, this is something we can very quickly and efficiently differentiate. On the right-hand side, it's an explicit derivative. The derivative of x with respect to x is 1. On the left-hand side, note this is one of the implicit derivatives, which means we differentiate that sine of y precisely as we would like to, cosine y. And by implicit differentiation, or think the chain rule, we multiply by dy dx. So immediately, we have a formula for dy dx. It's 1 over cosine of y. But note, this is not quite what we're looking for, right? We want to find the derivative of arcsine of x, which means our formula should only involve the variable x. So could we somehow use the fact that sine of y equals x to rewrite cosine of y? And the answer is absolutely. All we need to do is draw a right triangle. Maybe you're noticing a theme. Sine of y equals x. So we're thinking y is an angle, and sine is opposite over hypotenuse. The Pythagorean theorem would allow us to determine the value of this bottom leg. So a squared plus x squared is 1 squared. So a squared is 1 minus x squared, which means a would be plus or minus the square root. Because it's the leg of a right triangle, it must be a positive quantity. And now thinking about what we want it to determine, a formula for cosine of y only involving x. Well, we get that immediately from our right triangle. Cosine is adjacent over hypotenuse, so the cosine of y ends up being the square root of 1 minus x squared. And that does it for us. We now have two new formulas which we can apply. We have a differentiation formula. The derivative of arcsine is 1 over the square root of 1 minus x squared. And because of this differentiation formula, we also have an associated anti-differentiation formula. The antiderivative of 1 over the square root of 1 minus x squared, something we certainly were unable to handle previously, is now quick and efficient for us. It's simply arcsine plus c. So these are two formulas we want to make sure that we are familiar with. Now that we've differentiated arcsine, let's see if we can differentiate the inverse cosine function. And this is a point where if we were meeting in person, I would be turning the floor over to you. And in fact, what I would like you to do is to look over and understand the approach and the method that we use to differentiate the inverse sine function and apply it to differentiate the inverse cosine function. So pause the video, give yourself maybe 4 or 5 minutes, and see if you can come up with an associated differentiation formula. So back to our previous approach. Starting off with this expression y equals arc cosine x, I cannot directly differentiate because I don't know the derivative for arc cosine. But we could take the cosine of both sides and rewrite this expression so that it's simpler, easier for us to differentiate. Now when we differentiate both sides with respect to x, because our goal is to find dy dx, the right-hand side is a explicit derivative. On the left-hand side, it's implicit. We differentiate cosine of y, which is minus sine of y, and because it's implicit, we multiply by dy dx. So dy dx, this expression we're trying to find, is minus 1 over sine of y. And as long as we can come up with a formula or expression for sine of y only involving the variable x, we will have precisely what we are looking for. And using the same approach as the previous problem, when we have this statement cosine y equals x, that's describing an associated right triangle, where we have an angle y, cosine is adjacent over hypotenuse. This right leg, using our previous work, would be the square root of 1 minus x squared. And immediately, sine of y, which is opposite over hypotenuse, is simply the square root of 1 minus x squared. So very quickly and efficiently, using this technique for differentiating inverse functions, the derivative of arc cosine is minus 1 over the square root of 1 minus x squared. And just adding that to my table of common formulas to the right, we would have minus 1 over the square root of 1 minus x squared is the differentiation formula for arc cosine. And I'll also note that we could write down a slightly different formula for the antiderivative involving antidifferentiating minus 1 over the square root of 1 minus x squared. But noting that we can simply pull that negative out front, we actually don't need another formula. The one that we have certainly takes care of it for us. And similar to what we did previously when we learned new differentiation and antidifferentiation formulas for exponentials and natural logs, we are in a perfect position to practice a few examples. We see 2 examples, one derivative, one indefinite integral. I would like you to pause your video and give yourselves, let's say, I don't know, maybe 4 or 5 minutes to answer these questions. Hopefully at this point you've paused your video and you've gone through some computations. So let's summarize together. If we want to find dy dx, we would differentiate, and because of a composition, we would use the chain rule. The chain rule tells us we differentiate that outside function arcsine. The derivative of arcsine is 1 over the square root of 1 minus something squared. We substitute in the inside function, 2x plus 1. So this is our inside function, which has been placed inside the derivative of arcsine. Then we multiply by the derivative of that inside function. And you certainly could do this all in one step. The derivative of that inside function will become the numerator, 2, and we're dividing by 1 minus 2x plus 1 quantity squared. In terms of this remaining indefinite integral, you hopefully note the comparison 1 over the square root of 1 minus t squared with respect to t with this new anti-differentiation formula. The only difference whatsoever is a 6, which is a constant we can pull out front, and the symbol we use for our independent variable, whether it's t or x, we still have that same associated formula. So if we pull out the constant 6, and we note that this remaining indefinite integral corresponds to our formula for arc sine. In this case, it would be arc sine of t, our independent variable. And all indefinite integrals get a plus c. So in our next video, we will go back to discussing inverse trig functions by defining the inverse tangent function, talk about some associated limits of interest, and then come up with differentiation and anti-differentiation formulas. So stay tuned and take care.